at least as far as that goes. Okay, so what were we talking about? Anyway, I think you guys are doing well in here. This is a hard class, and I know everyone's schedules are really overloaded. So I don't want, if anybody gives up, I'm gonna be angry. Don't give up. Those of you that did well. Oh yeah, let me yell at the other people. Those of you who did well, I don't want to see any laurel resting happening either, right? Like, oh well, I have this totally wired because I got a 47. Like, okay, well, there's a whole 2/3 of the class left to go. Don't get complacent. What were we talking about? Talking about matrices. In section 3C. So remember that a matrix we defined as an object A, J, K. It goes from 1 to M. It goes from 1 to N. Where we're keeping track of the entries, preferably with commas, of course. I mean, Stathis is a physicist, right? So he's kind of a different take on notation. You don't have to. I mean, if I was using letters, I would just use letters. But when I use the numbers, 1, 1, and 11 aren't distinct in my head, right? So, M1. I mean, yes, in my own work, I would call this the matrix A. But let's pretend. Okay, so the big theorem last time is that we every linear transformation, every linear map has a matrix. And I think I told you that the way you get that is you fix a basis for V, V1, Vn, and you fix a basis for W, W1 to Wm, and then you calculate the kth column matrix by using T of Bk is equal to AK1, W1. I got this backwards. It's supposed to be like that. Right. So in a matrix for a linear transformation, this column comes from T of V1. This column comes from T of V2 all the way down to T of Vn. Right. The image of every basis vector produces a column in the matrix that represents the transformation. Right? It's one of the core ideas of linear algebra is that linear transformations have representing matrices. Yep.
So if you wanted to express W derivative V, would it be like, how would the matrix change?
If you wanted to go the other direction.
Yeah.
So, okay, you have to make some huge assumptions about like, so if you had a map going the other way.
Oh, so we're going from V to W.
You'd have to go from W to V. So you have to reverse the map, which probably, it would be no matter what you did, it would be a different map. So this is not something that's like a reversible process. Yep.
What does a matrix like tell you about the linear map?
That's okay. So that's a good question because Axer sort of has avoided the question so far. So let me show you what it does. I'm going to give you a little preview of why you do this. Okay. So I think last time we showed that the derivative map from P3 of F to P2 of F. I think we showed that the matrix for this was something like 0, 0, 0, 1, 0, 0, 0, 2, 0, 0, 0, 3. Did we do that? Okay, so this is the matrix that represents D. Now, suppose I just had some polynomial in P3, P in P3 of F. What I haven't shown you yet, and the reason why we can't do this yet, there's a way of thinking about any polynomial in P3 as a vector in R4 or F4, right? If I wrote down some polynomial here, I know that P of Z is equal to A0 plus A1Z plus A2Z squared plus A3Z to the third. That's just what it means to be in P3. Okay. I can take D and apply it to P. And what I get is, let's see, that disappears. You get A1 plus 2A2Z plus 3A3Z squared. You take the derivative and you get this out the other side. Okay. None of that involves the matrix at all, and it seems like what use is the matrix? That's, I mean, it's an obvious thing to say, like, who cares, right? Fine, there's a matrix. The point is, once we learn about isomorphism of vector spaces, we're going to say, well, look, this 4-dimensional vector space right here can be thought of as being equivalent to this. So this is called coordinates. We haven't learned coordinates yet, or vector space isomorphisms, but the idea is whatever's in this slot keeps track of what the constant coefficient of the polynomial is. Whatever's in this slot keeps track of the coefficient of the z. Whatever's this is keeping track of the coefficient of the z squared. So if this thing is sort of a renaming of this object, so these objects, we're going to introduce the idea of isomorphism, which is renaming, right? So these things are the same object under a rename, right? The same information is here. There's 4 choices. They're ordered in the way that they come, right? So if I took P, or sorry, the derivative operator and apply it to this, I get out A1 plus 2A2Z plus 3A3Z squared. What object is this? Maybe I should put it over here. This thing under the action of B turns into A1 plus 2A2Z plus 3A3Z squared. What vector should that be related to? Well, this is a polynomial in dimension 2, right? There's 3 things that are being kept track of here. An A1, an A2, and A3, right? So the vector that this sort of represents, or that represents this thing, or is equivalent to it, looks like this. This object is a polynomial of degree 2 or less, which is a 3-dimensional space. The coefficients are A1, 2A2, and 3A3. So this is the thing that comes out the other side under this identification. So what does the matrix do? The operator, the map, took this polynomial to that map. Well, it turns out to be the case that if you took this vector and you multiply it by this matrix, you get that vector out. So what happens in the matrix land is that if you took this matrix and you multiply it by this vector, that's the vector that comes out. And so what the matrices let you do is they take sort of these hard to understand linear maps, you slide them up into vectors, apply a matrix multiplication, and then you can come back down to the original space at the end. This is the basic idea of what it means to be an isomorphism. This is the core idea of linear algebra, right? So we are studying matrices because ultimately we're going to build the machinery to make this move make sense, where we go up to like some kind of F4, apply a matrix multiplication, and then come back down again. But we don't have this map yet. This isomorphism, this is the content of 3D. And once we know isomorphisms, we can talk about these things are called coordinates. So coordinates, I think, show up in 3E. Okay, so this is sort of the future, is to make this picture make sense. So we got to go ahead.
Just like how, like, you know, that condition corresponds to that.
You just, because what you're saying is, okay, I just imagine, I mean, there's a function that does it, is the thing, right? So it doesn't actually matter how I set it up, as long as there's one spot where constants go and one spot corresponding to the coefficient of the z term and one spot corresponding to the coefficient of the z squared. And as long as I'm careful about the way I set that up, there's the constant, there's the z, there's the z squared, there's the z to the third. You can go back and forth easily if I tell you you can do that, right?
And if like one was gone, then
There'd be a 0 in that spot. Yep. Yeah, I mean, motivating this stuff is important, right? Like the reason we're going to spend time talking about matrices is I need to understand matrices to even begin to make this picture make sense. The matrix that represents the transformation means that object makes sense. Then we're going to have to figure out why this move makes sense, which is called isomorphism. And then we'll have to talk about how coordinates work with respect to a basis. So all of this is the machinery that we need to do this, which is really secret. Like I said, this is kind of like letting the air out of the balloon a little bit, because you're saying, oh, well, secretly, in order to do abstract linear algebra, you could just have done abstract, You could have done linear algebra and Fn instead. That's the secret, right? Is that anything you can write down as a linear system can be thought of as vectors being acted on by matrices. That takes a lot of theory to build up, like why that works. Now, that make sense? Sort of as a motivation for why. Okay, so what are we actually doing besides letting my notes blow all over the classroom? It's a mess. Okay, so this is what we want. We want that map to make sense. We want coordinates to make sense. We want matrix multiplication to make sense. Good question. Oh yeah, I guess I should tell you that he also has a notation for this that he calls, I don't know if it's the right kind of fancy M of T is the matrix of T. Okay, so we didn't actually write this down last time, but you guys all know how to multiply, or sorry, how to add matrices. So I'm going to give you the mathematician's version of how you define what it means to add, like how matrix addition works, which looks like this: A JK plus C JK. That says a matrix. I guess I put JKs here too. That's saying the matrix that has these entries where you vary over these indices, the way that you add things together is you just add those entries together. AJK plus CJK. And that, so why would you do this? This is saying a whole matrix plus another whole matrix. The way you define addition is you go entry by entry. That's what that means. Now, this notation is preferable to the alternative, because the alternative looks like this. And in fact, if you've done anything out of earlier linear algebra books, you've seen stuff that looks like this. A1, 1, up to A1, and down to AM1, over to AMN, plus C1, 1, up to C1N, down to CM1, over to CMN, is equal to A11 plus C11, A1N plus C1N, AM1 plus CM1, What is life but repetition, right? This is kind of a long-winded way of saying what this says. This compressed notation is nice because it tells you the rule, like the entry by entry rule. Well, I have to write down these crazy arrays where you show how the pattern works.
So AJK is a single element.
AJK is a single element. AJK varying over entries J and K means run over all of the entries possible, right? So this is the entry. This says run over all of the entries. From J goes 1 to M and K goes 1 to M. Right. So the only reason I'm doing this is not because I want you to do this. I'm just trying to help you appreciate why this compact notation is useful, because this gets exhausting. In fact, Axler himself just gives up on it after a while. So he just does this. Okay. So what does that mean about matrices? When can I add matrices exactly? Well, they have to be the same size, right? This rule requires that I have matrices at the same size to add. Okay, we're gonna have a little baby theorem now. It's a little baby one. This is not a hard one. You guys can tell me what I mean here. So we define what it means to add matrices. What does that statement say? What is M of S plus T? No. What's this M? This fancy script M that I'm writing in the front of things. I just told you. I meant the matrix of, right? So in words, this says, and you have to be able to read the words here, right? This is why he's using fancy script M's. The matrix of S plus T is equal to the matrix of S plus the matrix of T. Right? So the sum of a linear transformation has a very easy matrix. The matrix that represents a sum is just the sum of the matrices. That's easy. It's easy to show. Now, unfortunately, we have to do the hard one, which is how do I represent the matrix of a composition? Because remember, I mean, why would I even want to know this? Well, these are a vector space, right? S plus T is a thing that shows up all the time. I frequently want to add linear maps together. If you allow me for a second to drift into linear algebra, or sorry, differential equations, every time you write down a second order differential equation, a linear second order differential equation in your 242 or 244 class, you're doing this. You're writing down two different things that are differential operators and adding them together. Right? You do it all the time when you're working with these vector spaces. In fact, this is so easy. Axer says the verification of the result above is left to the reader. Now, let's talk for a second about culture here, mathematical culture. When an author leaves something to a reader, let's erase the word easy here. Let's get that out of there. When an author leaves something to a reader, they actually expect you to do it. He expects you, when he leaves you to a reader to show this is true, to sit down with a piece of paper and work out why it's true. Now, I'm not telling you have to do that. I'm going to tell you that I encourage you to do that. So when you come across a statement where he leaves it to you, it is your, I mean, you go read the introduction. He wants you to do this. He leaves it to you. Try to build this argument. He trusts you. Better for worse, trust you. So do it. When you get stuff left to a reader, go do it. Now, I'm not saying it's necessarily easy. Some of the stuff I've left to the reader in the papers I've written have been like, pages of computations that are so boring that I didn't want to write to the paper. And then you leave it to a reader expecting that nobody would ever do it because it's so boring. But yeah, in a mathematical book like that, when stuff is left to a reader, it's your responsibility to make sure you understand why the argument works the way it does. Okay. What do we do about products and maps? What we'd really like to be true is that I could write down a statement like this, right? That the matrix of a product would be equal to the product of the matrices. So we want, so I guess from here, we have yet to define matrix multiplication. So we have yet to define matrix multiplication. And I think I told you guys last time that there's a lot of different ways to think about multiplying matrices together. In fact, there's one I didn't show you where you just stuff one matrix inside of the other one. And that's called the Kronecker product. There's all kinds of ways to multiply matrices. We want to choose. We want to choose a matrix multiplication. I know that seems weird that I'm saying we get to choose the way matrix multiplication is set up, but we literally are choosing a matrix multiplication. We're forcing this operation to have the property that we want. We want to choose a matrix multiplication so that the matrix of ST is equal to the matrix of S times the matrix of T. I really want this to be true. Okay, so I need to come up with some definition of matrix multiplication that makes the matrix of the composition equal to the product of the matrices that make up the composition. And it's not necessarily something that just, it's not made this way. It doesn't just come this way. We have to build the multiplication that does this. So this seems kind of weird, but this is really important. I said last time, part of the reason why the matrix multiplication algorithm is so strange is because it's precisely the one that makes this happen. That the matrix of a product of linear maps is equal to the product of the matrices in exactly the same way that this rule holds. The matrix of a sum should be the sum of the matrices. If if I want to do math and have it be nice, it had better be the case the matrix of a product is equal to the product of the matrices. Okay, well, I have one easy product that I can cook up. What should this be? So here's the first thing we'll talk about. What is this? Where lambda is a scalar. I bet you could just guess what that has to be. The matrix of a scalar times a linear map should be, if anything is right in the world, this should be the scalar times the map of the transformation. This is another one I think that the verification of the result above is also left to the reader. Really trust you. So we need this because the sum and scalar thing are going to be a big part of how we build what happens over here. And unfortunately, now we are right on the edge. The handing your exam back sort of changed my ability to do this today. Let's do one last definition and we'll be all set up where next time when we come in, we're going to build matrix multiplication. We're going to talk about composition and we'll be on our way to talking about making that derivative map I drew over there with matrix multiplication make sense. So the last definition for today is this guy. Which is m by n matrices with f entries.
So it's not a finite amount.
What's that?
It's a finite amount.
Sorry, I meant with entries in f. M by n matrix has m times n total entries, but yeah, with entries in the field. So it's a matrix of numbers, right? This is scale. The matrices have the same field that the vector space does. That's important. If I'm in a complex vector space, the matrices will be complex numbers. If I'm a real vector space, the matrices will be real numbers. Okay. All right. So we're basically all set up. I would encourage you guys maybe to read ahead slightly because page 74 and page 75 is the and page 76. That section is the construction of the single most important definition in translating this stuff into Fn, which is how we set matrix multiplication up to make this happen. And we're going to start by assuming that this holds and prove that it gives the matrix multiplication that we've already learned like 6 times in our life. All right, see you guys next time.
And then after the end or whatever, equal to the set of all linear transformations.
Actually, yes. In fact, so that's actually that's actually a bijection, right? That every matrix is a linear map. It induces a linear map from m-dimensional space to n-dimensional space, and every linear map from m-dimensional space to n-dimensional space has a linear map that represents it. So up to isomorphism. What's up?
Just wondering.
It's weird. Yeah, why not just use regular old like M,
Yeah.
M, N,
I've been using that.
M, N, F, right? I'm going to
Yeah.
mention that this is the more standard notation next
Yeah.
time. Yeah. It's a weird, I think it's weird, man. I don't know what it is. Oh, wait, did I record that?